So we've learned the rules for alkane nomenclature, and now we're going to take those rules and add on a bit in order to apply it to alkenes. So as a quick reminder, alkenes are alkanes that have at least one double bond, and they are called unsaturated because they do not have the maximum number of hydrogens, and each double bond is considered a degree of unsaturation. So a lot of the rules for nomenclature look the same, but the first thing we have to change is the ending of the name. So all alkanes end in ane, and all alkenes end in ene. So butane becomes butene if it has a double bond, and hexane becomes hexene if it has a double bond. So again, most of these rules are going to be the same as alkane nomenclature. You're still going to count the largest parent chain, but you're going to prioritize it so that the double bond gets the lowest number. And your numbering has to include both carbons of the alkene in the parent chain, and it's always numbered based on the lowest. So for example, here I would go left to right in order to give the alkene priority. Notice that both of the carbons that the double bond is between are in the parent chain, but we would call this 2-pentene. We always call the alkene by the lower carbon or the carbon it starts on in the chain. And then you're going to determine the number and the types of substituents, just like alkane nomenclature. And then you're going to assemble the name and you're going to place the alkene carbon number either in front or in the middle of the parent chain name, but it always comes after any other substituents. So let's practice with this molecule here. I'm first going to number it from the right to the left in order to give my alkene the lower number because it has a higher priority. On carbon 4, I've got a methyl group, it's a CH3. And so the way that I would name this overall is 4-methyl, and then I would do 2-pentene. Alternatively, you could do 4-methyl pent dash 2 dash ene, and you're going to see me do it both ways. When names get more complex, sometimes putting the number in the middle just is easier for clarity's sake, but when they're pretty straightforward like this, it also gets put at the front and it's still pretty clear what it represents. If you've got molecules with more than one double bond, you're still going to number it the same way. You're going to change the ending of the name to "ene," but in front of it, it gets a prefix, similar to the prefixes if there's multiple substituents. So for example, 2 double bonds, diene, 3 double bonds, triene. So it's the same prefixes as before, but still you have one number for each double bond. So for example, this molecule down here would be 1, 3 pentadiene because the double bonds start on carbon 1 and 3. So I have two numbers for the 2 double bonds, di to represent the 2 double bonds before ene. You could also put it in the middle of the name like this. And over here with 3 double bonds, similar process, 1, 3, 5, hepta, because the parent chain has 7, and then triene to represent the 3 double bonds at these 3 carbons in the name. Cycloalkenes, again, similar to cycloalkanes, except you prioritize the double bond or bonds when numbering your ring. And so the goal is to reduce the numbers on as many substituents and double bonds as possible. But if you're numbering a cycloalkene, one of your alkenes should always start on carbon 1. So for example, if I pick this this alkene over here, and I'm going to pick one of these carbons to be carbon 1, I'm also going to pick the one that has the substituent in order to minimize the number on the substituent and on the alkene. When I do that, I cannot go this way because this bond has to be consecutive within my parent chain. So it has to be 2, 3, 4, 5, 6, right? I need both the carbons of this alkene to be consecutive in my parent chain. And I have a methyl group on my first carbon. So when I go to name this, it's going to be 1-methyl. And then if I put the numbers in front, it'll be 1, which is the first carbon for this alkene, and then comma 4, which is the first carbon for that alkene, cyclohexadiene. Alternatively, you could put the numbers in the middle, 1-methyl, cyclohexa dash 1, 4, diene. So same rules, you just have to be strategic about your numbering to minimize the numbers on both the alkenes and the substituents as much as possible. So the general outline for these names looks the same as the others. So here's just a summary. You put your numbers and your substituents, your parent chain, and then your suffix for your functional group. In this case is ene for alkenes, making sure that you always include a number for where that alkene is, even if it's on carbon 1, because we have to indicate to the person reading this name where the double bond is located in the molecule. So that's the general rules on how to write alkene names, and we're going to get a little more complicated and precise with them now. Some really quick common names for alkenes. There are not as many that you have to remember for the alkanes, but sometimes ethene, propene, and butene will just not be shortened, and you'll have the YL name included, so ethylene, propylene, and butylene. Those are just some common names that are used in sort of the chemical community, I guess. The other key one is that carbons that directly participate in a double bond are often called vinylic carbons, and carbons that are one place removed from the double bond are often called allylic. And this isn't specifically important for nomenclature, but is important for how we refer to different carbons within a molecule. So, alkenes can also be complicated because they can have things called stereoisomers. And stereoisomers are when atoms are connected the same way, but they are arranged in three-dimensional space differently. So maybe in a previous class, you've heard of cis molecules or maybe trans molecules. This has to do with the arrangement of substituents around a double bond. Cis molecules are when identical substituents are on the same side of the bond, so not bonded to the same carbon, but bonded to the same side of the double bond, because remember, a double bond has that sp2 geometry and is trigonal planar, so it's flat. Trans configurations are when those identical substituents are on opposite sides of the double bond. So you can see here that in the cis conformation, yellow on one side, red on the other, and you can see in the trans conformation that they lie on opposite sides of the double bonds. If a carbon participating in a double bond has two identical substituents, like two hydrogens, for example, you cannot label them as cis or trans because I can't assign priority or say that either of these two substituents are on the same side of another if it's the same thing on both sides of that double bond. So if one of the carbons in a double bond has the same substituent as both of its substituents, then this next sort of section we're going to talk about does not apply to those double bonds. So cis and trans configuration nomenclature is really nice when substituents are the same, or we can consider them similar, like two similar carbon groups. But when we start adding more complicated factors around our double bonds, the nomenclature falls short. And so instead, we have a different system called the E or Z system, which is necessary for ranking different substituent priorities like this. When I get something like a bromine or a chlorine, well, how do I decide which one of those is more significant or has a higher priority? Either way, for both cis and trans and E and Z nomenclature, we add the stereochemistry in our name at the very front. The E and Z always go in parentheses, which we'll show you some examples of, and cis or trans just get added to the front with the dash. So the E and Z nomenclature notation is definitely more complex than just cis or trans, but it also can be used for far more alkenes. So E is when the higher ranked substituents are on the opposite side of the double bond. So for example, I've got high on the top here and high on the bottom here, and therefore the highest priority groups are on opposite sides of that double bond. This stands for entgegen, which means opposite or separate in German. And if E is when the two substituents or highest priority substituents are on opposite sides, then it would make sense that Z is for when the substituents are on the same side. And so it might look like this, where my two higher priority substituents are on the same side of the alkene. And this is short for zusammen, which stands for together, essentially, or means together in German, where these names originate. The easy sort of cheeky way to remember this is that Z is when the highest priority substituents are on Z same side. And you laugh now, but I learned that over a decade ago when I first studied organic chemistry, and I'm still using it today. So let's really dig into how do I determine the ranking of substituents. We've talked about how E is when the higher ranked are on opposite sides of the bonds, and Z is when the highest ranked are on the same side of the bond, but we haven't talked about how to rank them. So first things first, the higher atomic number will always outrank the lower atomic number. Now, when you rank them, you instead have to look at the ones that are bonded to the same carbon. So sometimes I like to draw this vertical line first to know I'm going to compare the two substituents on the left to the two substituents on the right, or the two substituents bonded to the same carbons. So if I compare bromine and fluorine, I'm going to look at the periodic table, and I can see that bromine has a higher priority because it has a higher atomic number. Bromine's atomic number is 35, whereas fluorine's is 9. Now I'm going to compare the two bonded to this carbon on the right. For this, hydrogen basically always loses because it is atomic number 1, and so chlorine is the high priority. So again, when determining priority, I'm looking at the ones bonded to the same carbon. Now, when I want to figure out E and Z, I kind of have to split it the other way, and I'm going to compare the sides of the double bonds or the substituents on opposite carbons. So in this case, high is on the same side as high when looking across the carbons. That would mean that the highest priority substituents are Z or on Z's same side. So to name this fully and completely, I would put in parentheses Z in front of the rest of this name in order to indicate that the higher priority substituents are on the same side of the plane of the double bond. Well, that's great, but a lot of these are organic molecules that have multiple carbons in them. And so sometimes you work your way outwards, like comparing these two, and they're both carbons, and carbon has the same atomic number. So how do I figure out which one has the higher priority? Essentially, you're going to figure out what's bonded to that carbon. So I'm going to look at this carbon first. And what I like to do is I like to sort of start a parentheses list of what's bonded to that carbon. Now, I don't need to include the carbon in the alkene because both of the substituents we know are bonded directly to the alkene. So I'm only going to look at what's uniquely bonded to this carbon, and it's 3 hydrogens in this case. So in my parentheses, I would just put those 3 hydrogens to indicate that that carbon on the top has 3 hydrogens bonded to it. Now I'm going to look down here at the bottom. What's bonded to this carbon? Well, bonded to this carbon, I have another carbon and then 2 hydrogens. When you do the parentheses like this, you're going to put them in order of atomic number, decreasing atomic number. So carbon would come first, this carbon, and then the 2 hydrogens that are bonded to this carbon. And now I sort of have a battle between these sets of parentheses, who's going to win? And it's the first point of difference with the higher atomic number. So the first one I'm comparing is hydrogen to carbon. And so that would mean this bottom one has a higher priority than this top one because carbon has a higher atomic number than this hydrogen. And so we would say that the CH2CH3 group here outranks or has a higher priority than this CH3 group. And so again, we're comparing the two that are bonded to the same carbon, and it could be anything over here, and then you would determine E and Z from there. But wait, there's more. You don't evaluate substituents one by one. You don't add together the atomic number to see which one's the highest. You just look for the first point of difference. So you don't add the atomic numbers, you just list them in decreasing order of atomic number, and then you compare. So an example of that might be like this. These are both carbons, so we're going to figure out what's bonded to each of these carbons. Well, bonded to this top one, I have an oxygen, which has the highest atomic number, and then 2 hydrogens, which would come next. And again, we don't count the alkene carbon because they're both bonded to that. The bottom carbon bonded to it has 3 more carbons. So on first glance, you're like, well, this one's got 2 hydrogens, this one's got 3 carbons, this one must be the higher priority. But that's not true. I have to look at the first point of difference. The first point of difference is oxygen versus carbon, which is why it's important to put these parentheses in decreasing atomic number, always starting with the higher priority atomic number. And oxygen has an atomic number of 8, whereas carbon has 6. So this top one actually would be the high priority, and this bottom one would be the low priority, even though it might look like it has a higher priority. We're not adding together the atomic numbers. We're just looking for that first point of difference, which means oxygen outranks the carbon. But wait, there's even more. Sometimes substituents can have other double bonds to other atoms, either other carbons or oxygens. And so, how do we make those parentheses for those types of substituents? So, essentially, if there's multiple bonds to another atom, it's considered to basically replicate that atom on the substituent for the number of bonds it has, which is really hard when you put it in words. So, I'll show you an example. We already did this top one here on the previous slide where we said it has an oxygen, a hydrogen, and a hydrogen bonded to it. When I look at this carbon here, when I go to compare, right, I can see that it has a hydrogen and then it's double bonded to an oxygen. Because it is double bonded to the oxygen, we count the oxygen twice, as if each bond gives that carbon one oxygen bond to, or one oxygen to sort of bring to this substituent priority fight. So when I go to compare these two, they both start with oxygen. So I'm going to cross it out and I'm going to move on to the next point of difference, right? So then I'm comparing hydrogen versus oxygen, which would make this lower one the higher priority and the top one the lower priority because of the two oxygens due to the double bond of this carbon to the oxygen. And remember, we only do this comparing when the two initial atoms are the same. So in this case, the atoms initially bonded to that double bond as I worked my way out were both carbons, and therefore I had to compare from there. If there's a difference right off the bat, then none of these extra steps are necessary. Okay, so let's do some quick practice without doing the full names, just determining E versus Z. So again, the first step I like to do is cut the double bond in half so that I know I'm going to look at the substituents bonded to each carbon separately and then look across the double bond. So if we start with the top left up here, it sometimes is helpful to write in this is a CH3 and this is a CH2 and a CH3. So immediately bonded to that alkene, it's carbon both times. So then I need to start putting in my parentheses. This carbon has 3 hydrogens bonded to it. Remember, I don't count this carbon because they both are bonded to that one. This carbon here has another carbon and then 2 hydrogens. So that would make this substituent here a higher priority because this carbon outranks this hydrogen. So that would mean this substituent would be high and this one would be low for the ones bonded to this carbon. Then I move on to the right-hand side of the double bond. Okay, if I make one step out, I'm looking at chlorine versus carbon here. That one has a point of difference right away. There's a chlorine directly bonded to the double bond. That's different than carbon. And chlorine has a higher atomic number, so it's going to have high priority, and this one will have low. Even though the substituent looks larger, right, we're comparing this C to this Cl. So now I'm basically going to cut the double bond in the opposite direction, and I'm going to compare across the top and the bottom. So low and low are on the same side of the double bond, and high are on the same side of the double bond, which means the substituents are on Z same side and makes it a Z configuration. All right, let's look at this one over here. So I'm going to cut the double bond in half, right? And then I'm going to look at each carbon individually here. This CHO group that you see like this, it looks like an alcohol that's backwards, but it's actually not an alcohol. If you drew it out, it would be an aldehyde in order to fulfill that carbon's octet. Just a heads up. Bonded to this carbon down here, I can only see one substituent, and that means the other one must be a hydrogen, right? Implied hydrogens are still a thing. So let's compare these substituents on the top first. So when I work my way out from my double bond, I run into a carbon and a carbon here. So that means I need to start my parentheses. Bonded to this substituent here, I have carbon, carbon, and then an implied hydrogen, so C, C, H. Bonded to this substituent, which I drew out for you up here, I've got oxygen twice because of the double bond, and then a hydrogen. So when they start the battle for priority, I'm comparing oxygen to carbon right off the bat. Oxygen will win, so that would make this high priority and this low priority. Now I need to look at the ones bonded to this second carbon of the alkene, and this one's a little tricky because it's sort of twisted sideways, right? Normally they're more horizontal, but you're still going to compare the things bonded to the same carbon first. Again, as a hint, hydrogen always loses, so this is going to be low, and the carbons and the rest of the substituent down here is going to be high. So then I cut my alkene across, and I'm comparing low to high on the same side, low to high on the same side, and so that makes this an E configuration. Let's practice adding this to the naming of an entire molecule. So when I go to number this parent chain, I preference my alkene, so I'm going to start it here. Okay, I can see that I'm going to have hexene as my parent chain, and coming off carbon 3, I have a methyl group. So let me start to write this name, right? It's going to start as 3-methyl, and then I have to put the number that my double bond starts on, 2-hexene, or you could do hex-2-ene. But I can't be done now because I need to determine the E and Z configuration of this double bond. So there's an implied hydrogen here that I'm going to draw in to help me. So first I'm going to split it so that each carbon is on its own side. And I'm going to compare the things bonded to each carbon. So this is a CH3 and this is an H. Hydrogen always loses, so this is high and this is low. Now I come to the next side. This is a CH3 down here. And this is a CH2. So now I need to make my parentheses to compare because they're both carbons bonded directly to the alkene carbon. This top carbon has a carbon over here plus 2 hydrogens bonded to it. And the bottom carbon has 3 hydrogens. Okay, so based on atomic number, this top substituent gets high priority and this bottom one gets low. So then when I cut my double bond the other way and chop it through the carbons, I'm comparing high and high on one side and low on the other side. That means that the high priority substituents are on Z same side, so the configuration of this will be Z, and I add it to the front of my name like so. All right, next and last one, I'm going to number my parent chain. Again, I prioritize my double bond. I've got a methyl group coming off of carbon 2, and my double bond starts on carbon 2 as well. So this is going to be 2-methyl and then 2-pentene. Right? Now, if I go to start prioritizing these substituents, I'm going to cut and split up the 2 carbons. If I look at this carbon on the right, I've got CH3 and CH3. Those substituents are identical. There's no way to assign priority between 2 CH3 groups. They have the same thing bonded, they're identical substituents, and so that means this particular molecule does not need cis or trans or E and Z because of the identical substituents bonded to the same carbon. So we'll get lots of practice with this, but hopefully it gave you a good introduction and an idea of how to add these layers of alkene nomenclature into our already existing rules.